of Jean-Philippe. But okay, so we are pleased today to welcome Jean-Philippe Malet from the IOST laboratory in Strasbourg. So he's a geoscience expert in remote sensing, and experts in the monitoring of geohazards also, and especially landslides, which is the topic of our webinar today. So first, I would like to introduce our project, which was implemented thanks to funding from the European Commission. So this is the Working Group Africa project. Maybe you heard about it. And the objective of this project was to train African trainers to process and use satellite data and services. So in total, we have trained 20 African trainers in 3 languages and 16 African countries. And we have developed, and also themselves, they have trained local trainees, reaching an amount, in fact, of 2,000 trainees in all these African countries that you can see here on the map. Hello. And so one component of the project was to raise also awareness regarding Copernicus in Africa through webinars in 3 languages. And so although the project has stopped now, we are continuing this activity dealing with webinars. And so with the cooperation of IDGEO, which is a training company in France, we are organizing these webinars. So maybe you had the chance already to watch and participate to the webinar dedicated to hydrology in Africa, space hydrology in Africa, and also a webinar dedicated to forest monitoring with the presentation of the biomass mission from ESA, and the Tropisco project, which is a project aiming at monitoring deforestation in the tropical forests. So all these webinars, you can watch them. You have the replay available. So if you want to access the replay, please send us a message. And just I would like to say a few words about the training resources that we have developed in the framework of this project. So you have the list of all the modules, starting with GIS basics and also some pedagogical methods, because the objective was to train trainers. And we have each module is 1 week long, 5 days long, and it includes lectures, but also exercises, and all the training contents are being hosted on a platform, on a digital learning platform. So you can have all the course material on this platform, the exercise, the answers to the exercise, the training session recordings. You have also resources with bibliography. And it is open to new users on demand, and not only to users and experts from Africa, but also users from the other parts of the world. So feel free to send us a message if you want us to create an account on this platform. So there are modules dedicated to basic topics, I would say, related to Copernicus, but there is also some sessions and lectures dedicated to thematics like health monitoring, but also forest monitoring, marine pollution, so a wide list of topics. Okay, so just maybe it won't be too long. I just wanted to show the last slide with all the entities who have contributed to this project, and there are European entities such as the Portuguese Space Agency, the Netherlands Space Office, the Northern Observatory of Athens. And so we were a group of a consortium of 12 institutions from Europe implementing this project in collaboration with African experts also who became campus trainers. Okay, so now what I would like to give the floor to Jean-Philippe. So there will be around half an hour presentation, I believe, and then we will have time also for questions. The objective of this webinar is really to have interaction with you and with the speakers. So please feel free to intervene after the presentation of Jean-Philippe, sorry.
Okay, hello everyone. I'm just launching the presentation and sharing it. 1 second. Okay, is everything okay on your side? Just putting in large screen. It's okay?
Yes,
because
yes.
I do not see you anymore. I just see my screen, in fact. Sorry.
Okay, fine.
Perfect. Okay, maybe I just have to do that. Mask. Oh, now what's going on? Yeah, okay. Well, so, okay, nice to meet you all remotely. So I am Jean-Philippe Malet. I'm a research director at the French research agency called CNRS. I'm a geophysicist, working mostly on natural hazard in more or less mountainous regions. So it's about landslide, about flash flood, about, well, everything related more or less to hydrometeorological risk. Trying to use both satellite information, in situ information from sensor models, etc., to try to better understand such type of processes, and try with the knowledge we have gained on this object to try to set up some, let's say, operational or pre-operational services to try possibly to anticipate them, or at least to deliver some additional information to people in charge of risk management. So what I will present to you is an initiative we have since several years about trying to produce a landslide hazard information system. It's in fact built around several projects, and the idea is really to try to combine Earth observation data models, more or less for kind of near real-time forecast or no-cast of landslides, both on the hazard component and for some aspect also to try to anticipate the impact they may have on different type of stakes, like buildings, like different type of land covers, etc., etc. So it's a group that is working on that approach with colleagues in Switzerland at University of Lausanne and a spin-off of the University of Lausanne called Terre, with colleagues also of the US Space Agency, NASA, and also some colleagues in Italy, more on the platform side. So why we set up these services is the idea of trying to see how we could anticipate such type of landslide. So we are not, you see the map or the photo behind. I mean, the question is not about anticipating one landslide, but if you have some extreme rains, how can we try to anticipate what you see behind? Okay, so several sources of sediments that more or less start from the top of the hill slope and then propagate more or less downstream, may possibly in fact connect to a river system. Then you have this sediment in the river, and you may have a cascade in fact of different chain of events, starting from small failure at the slope, propagation, and then more larger propagation as a flood with a lot of sediments in the river channel. And the idea is really here how space-based Earth observation data can help us by combining several types of information coming from this satellite in nowcasting this type of processes. And the nowcasting is done by some simple models where we also use some space-based information about rainfall estimates of the triggering by rain. And the idea is also to see how we can propose some products which can support hazard and risk assessment. And even because some of this work was also totally in connection with World Bank or the Asian Development Bank to see how we can anticipate with products to do some disaster risk financing, DRF products in relation to that. So the idea is about really shallow landslide, okay? It's not the full spectrum of landslide that we want to track, but really such type of events, more or less shallow one, relatively rapid, relatively instantaneous when they start after a big rain or an extreme rain. And you may have different configurations. So a small part of a slope that starts, and then, okay, the volume is relatively small, and then you do not really reach, you do not have a long propagation of the sediment. So it's relatively, let's say, well, the length, in fact, the propagation is small. Then you may have, in fact, other area where you have several sources at the same time that triggers, I mean, the same rain can trigger several landslide on one slope with different size then of the event. And then, okay, you may have such type of situation as well, where then you connect directly to some buildings, and you may have then some disaster. Okay, here we were in a relatively remote area, and then, okay, you see the consequences of such type of event after some extreme events. This is an example in tropical area in Puerto Rico, and this is an example in Brazil with even more landslide that have been triggered and that affected some buildings. So the key point is that, okay, what can we do, in fact, and how can space data help us to anticipate such type of phenomenon? When we look at that, we need first to anticipate where are the possible area where the landslide may occur. So this is what we call identifying the source area of the different sediments. So we have, most of the time we use inventory of past events that have been triggered, and it's very interesting then to use EO data and space-based data to try to construct some inventory of all the landslide that have been triggered on an area, and then see, because we have the local spatial information of the direct location, anticipate then the future location using what we call some susceptibility models of the source area. Then once we have the source area, I mean, the key point is that maybe not all of this area will propagate. I mean, the sediment will not propagate everywhere, downstream, downhill. And the key point is to say, okay, what are then the volume in relation to the triggering event, then to the type of rain in terms of intensity, in terms of duration of the rain, in terms of accumulated amount of water that is being trigger that is being that is going onto the slope, and according to all these characteristics of the rainfall, we may have different configuration of volume that can propagate downstream. So this is the second aspect we need to anticipate, and we need to do that by using some forecasting models. I will come back to that later. And then finally, the point is, once we have the volume according to the rainfall, okay, we need to anticipate what could be then the propagation path, so where it will go, and also what will be the distance of runout, the maximum extent, and also the maximum depth of the area. So this is relatively critical because, okay, because you have this propagation path, then you may directly go, in fact, to the different stakes and the different buildings and the different infrastructure that could be destroyed or damaged according to the propagation path. So this is exactly what we plan to do with this system, trying to cover these three aspects by combining several types of information. And to do that, we are currently implementing what we call the landslide hazard information system to nowcast landslide hazard and to identify when and how it can be related to the exposed infrastructure and the different population. So it's a service that is currently implemented on platforms. So there is a running service that you can use by going to the ESA JEP geohazard exploitation platform. It's a thematic platform about, let's say, ground deformation and everything related to risk related to ground deformation. And it's also currently being implemented on the Terre research infrastructure in France to also support it on the long term for the science and operational community more at the scale of France, but that could be also offered, in fact, to other type of community. So in the system, in the app, in the application, we have several subsystems that we have called LHIS catalog, LHIS hazard, and LHIS impact. This catalog is really to try to put together techniques to create the inventory of past landslide, to detect new ones, and then to look at the first aspect I mentioned before, to try to estimate where the landslide may occur, so go to the detection of the source area. Then we have the second component of the system, this hazard, which is really the models. In fact, we leverage on the information we have in this catalog, and then we model according to the rainfall that we may nowcast, we model and forecast the landslide hazard and go to the estimation of the propagation and the runout and the different depths that we could have with the sediment. And then finally, the additional point, we can by combining information with the element at stakes, the exposure of the territory, information on the buildings, or even information on the population. The idea is to anticipate some quantitative assessment of the possible impact, more as a kind of scenario to anticipate what could be, in fact, the possible damages that could be defined. So it's organized like that. In fact, in terms of workflow, we are combining together this landslide assessment module with a landslide impact assessment module. We are using different type of data for the different component of the system to try to nowcast this landslide event from extreme rain. And the outputs are different maps to perform hazard assessment. Susceptibility analysis is the source area. Then we have the scenario-based analysis is according to the rainfall, okay, what could be the volume that could be released and go downhill. And then we have the hazard rainfall nowcast, which is in fact the propagation maps that we could get. And then this is used by cross-correlating with other information to do to create some impact maps with different methods, okay, to have an index of the possible damage, and even if we have some cost according to the buildings or to the infrastructure, okay, to eventually even have a kind of rough estimate of possible cost of the damage. So you can use, of course, this different module independently. You can only create the susceptibility map and not go further, etc. So it's totally modular according to what are your expectation and your application. And what we do as well is that we have leveraged all the information by combining science models from different science teams participating to the working group. We are using the LHASA model to do the estimation of the volume of sediment that can be released. We are using another model to do the propagation part, which is called FlowAir by the colleagues from Switzerland, etc., etc. So, I mean, this is based, in fact, on some more or less state-of-the-art models coming from different groups. So currently, we have started to implement this system in several regions. The initial development was in Africa, in North Morocco, in the Reef area. So it's more or less a 3,000 square kilometer area. Because what you can do with the system, it is a territorial application. You will see then later you have some maps. And the idea is not to work at the scale of one sub-catchment or small landslide. It's really to be able to cover, let's say, a region and try to anticipate the hazard related to landslide from extreme rain. So we started with some application with some funding from the World Bank together with some stakeholders in Morocco, and we developed in fact the proof of concept over this area, and then we had some demonstrator application that we are currently finalizing. There is one, I forgot to mention it, but there is one also application in the French and Swiss European Alps. We have a demonstration with the support of CNES and the Space Climate Observatory in Rwanda, and we are currently starting a project with colleagues in South Africa, in a region in the eastern part of South Africa, highly affected by landslide. So we go from a proof of concept to let's say more or less relatively high TRL demonstrator, TRL 7 to 8, to have some operational services according to this development since a few years. Okay, so I will start with presenting the Morocco use cases, because this is the one where you can really have the full picture of the different system. So the first point was to set up the creation of landslide inventory, mostly from optical data. It's still relatively difficult to use SAR data for detecting landslide because the resolution is not sufficient. There are a lot of aspects about you are decorrelating the signal coming from SAR satellite because I mean, the landslide is moving too fast, etc., etc. So optical information at medium resolution like Sentinel-2 or very high resolution like Spot, Pleiad, and other very high resolution optical satellite are really of use for such type of application. And the idea is to set up some automatic change detection technique. We have a system called Aladdin and now some other tools based on AI to be able to learn an AI model from past landslide events and then detect, in fact, by change detection technique and AI, the new landslide that have been detected over a region to build such type of inventory where you have then the location of the new landslide. Based on that, we can then anticipate the future source area. And for that, we define some susceptibility map using some susceptibility model where we are able to correlate the location of the landslide coming from the satellite information to some static parameter describing the landscape. So it's mostly lithology, it is the land cover, it is information about the relief, etc. But in terms of different aspects, the curvature of the slope, the length of the slope, of course the slope angle, etc., etc. And based on that, the idea is to train a simple AI model. We know the source area of past landslide, and we try to predict the future occurrence of the landslide based on what we have seen before. Okay, because we have a certain combination of slope, geology, land cover, etc., etc., of past landslide, we can anticipate and predict the future location of the next one, because more or less, in fact, we have the hypothesis that we have the same type of conditioning factors. So there are several techniques to do that. We are using a random forest machine learning approach to set up this system. And this is done online, in fact, within the application. And we can then, based on the update of the different landslide information coming from the satellite, so the new inventory, we can refine by rerunning then the susceptibility AI model. We can get access to possible new landslide source area that might be triggered in the coming weeks or etc., etc. So it's not a prediction. It is currently sorry, there was some noise behind that. Sorry, but, I have a lot of echo from someone. Sorry, maybe someone has a mic. Okay, well, I continue. So it's not a prediction of when a landslide will occur. This is just, okay, the location of the area where a landslide might be triggered. Okay, so it's really the location of the source area, and if you have a big rainfall coming after, these areas are the most susceptible, in fact, to trigger the propagation of sediments. And we are able to class then with some metrics this information in low, medium, high, or very high probability of having access to, of having the possibility to trigger some landslide over this area. So it's done at the regional scale, you see, but you have a high resolution then, because this is a zoom over this area, I mean, the prediction is done at a 20 meters spatial resolution to have some details, let's say, of the area. Then we need to be able to compute the propagation area, and to compute the propagation area, we have currently only the information about where it can start. So it's the information about the source area coming from these maps. And then the idea is that we know the topography, we know the type of slope downstream of the source area, coming from the topographic information. And based on that, there are some models that can estimate the maximum propagation of a certain volume of sediment. So the key point is then to estimate the volume that can be released here, and then based on some scenario, you can anticipate, what could be the different, the maximum runout, and this is currently what is being done within the system. You have a conservative scenario where, you calculate the maximum runout, so basically, the maximum length of the propagation path of the sediment downstream, and you have a less confidence interval, to have some estimate and some scenarios. So this is the type of parameters, in fact, we use in the model, in fact, to try to anticipate this propagation. And then from an information just related to the location of the source area, that are this area, we can then estimate, how the landslide can propagate downstream. And to do that, we have calibrated, in fact, the system of our observed and past landslide. The blue area are here, the real extent of the landslide from past events, and you see that at first order between the start as a source area to the propagation, more or less you have an idea, of where and the sediment can travel, at always this spatial resolution of 20 meters. And of course, you can do that then at the large scale of the region. So this is the susceptibility map of the possible source area. You have a rainfall event, and you have a certain amount of rain that trigger a certain volume of sediment, and then you have the runout that is calculated. So source area, the runout, and the propagation. And based on that, then you can see, this could be an area. It will be connected to a river. Maybe, you have some stock of sediment in a river. It can be exported and later as a flash flood with all this sediment connected in the river. Or you have maybe a road or a building or a small village here, and then you see, there was this source area far from the village, and the buildings, but with the estimation of the runout, here could be a hotspot of possible impact and damages in case of extreme rain. So that's the main idea of this combination of source area and propagation. And then the idea was to nowcast all this system, because now we have a system which is calibrated on real events, on past real observed events. So it has been calibrated for a certain region, and then we really need to use the system as a no-casting system. And based on that, we can use some spatial nowcast of rain coming. There are some products mostly proposed by the US. It is the IMERG precipitation nowcast, which is a global product, freely accessible. It works at a resolution of 500 meters, so it's more or less compatible, in fact, to what to the estimation of the small site of the landslide. And based on that, we can do some specific calculation to take this information and nowcast of the rain, establish some criteria based on some calculation of cumulated rainfalls and triggering of past events according to this rainfall, and then anticipate that, okay, if there is an forecast of a certain amount of rain, then we pass a threshold, and then we have a certain volume of sediment that can be released, and then that can be propagated downstream. So this is how the nowcaster is working, and we have implemented that online. The system is running daily, and based on the calculation of this antecedent rainfall index, which is the criteria we use to trigger the fact that there will be a landslide or not. Okay, you have a map with the information about the rainfall information. Here there is a big rainfall coming, in fact, in the area of North Morocco. And then you have the information about the landslide sources that can be activated, let's say, and then information about the propagation. Okay, so this is in fact the runout extent based on the information coming from the rain. Of course, we disaggregate then the rainfall information to let's say put it in relation, in fact, with the size of the prediction model at the 20-meter spatial resolution. Then we have the final module called LHIS impact. Now we have the information about where a landslide can occur. We have the information on the rain. This rain is triggering sediment. We have the information on the propagation. Okay, now we can have this information and link it to the infrastructure and the different buildings. And there is a method called PDI, Potential Damage Index, okay, that will leverage, based on multi-criteria analysis, information about these buildings. So we are using land cover information over the region. We can use other type of information where, in fact, the land cover is not really precise enough or at high spatial resolution. Then, okay, you can also possibly integrate other information with more details. In fact, mostly if you are also working in more urban area and not only rural ones, okay, where you need maybe more details, in fact, about some classes of the land cover. And you can also integrate information about the number of inhabitants or the classification of different type of population within the region, still over the area of North Morocco in that case. And this is aggregated, in fact, in a multi-criteria model that currently will then estimate the potential damage that is possible according, in fact, to the scenario of the different landslide that has been triggered, and if it is connected or not to the sediment. So this is also implemented within the platform. So you have access then to an information about this value of PDI, potential damage index, with a ranking between 0 and a certain amount. And this is a kind of proxy of a risk map where you can anticipate as well, where you have mostly the main area at risk from that no casting of landslide. So it's available. You have access to the maps, but you have also access to some indicators that are aggregated at the scale of the municipality, because the idea is not here to have mostly information at the really pixel scale. It's more, in fact, to have a kind of aggregator as an index, municipality by municipality, township by township, let's say, because this is the main information that was expected by the stakeholders, okay, to more or less rank, in fact, the different area and municipality according to the risk potential. So this database is also produced automatically. You have an information about the possible number of inhabitants that could be affected, the number of buildings, etc., etc. So all this information is part of the database, and you can also map, in fact, this factor on the site. So currently, this system has been developed as a proof of concept from Morocco. And we have now some new developments ongoing, and we have a more, let's say, robust and consolidated approach. We have other models, a little bit more complex to be generalized, okay, to several countries. And we have now some running demonstrator for some region in the European Alps. We have a running demonstrator that will be released in next spring in Rwanda, and we start to implement a similar system in a sub-region in South Africa, as I was mentioning. And the main point is by this new application over this area is to work more on higher spatial resolution of the prediction of the different landslide over this area. So that's the situation, and I'm very happy. If you have some question, I could answer to all of them in the discussion. Thanks a lot.
Okay, thank you very much, Jean-Philippe. For this is really impressive, this system with all the modules being connected together. So, are there any questions? Maybe I can ask one or two to start the discussion. So you said that to create the inventory of landslides, you were mainly using optical data, and I was wondering, do you need what kind of methods do you apply? Is it change detection methods? On which type of index, or do you use time series? Do you need time series, but then with what temporal resolution? So this is the first question that I would like to ask regarding the module dedicated to the creation of the inventory and the detection of landslide with based on remote sensing data.
Yeah, exactly. Okay. I mean, there were two approaches we have. The initial approach of the Morocco was only to process 2 images before an event, after an event. So it was more change detection over 2 days, in fact, by training an AI model on where a landslide has occurred and try to anticipate and then generalize the information on other area. And then a new approach that is currently implemented on the Rwanda use case, connected in fact to all these developments, is what you have here below, is that we process now a real time series of, and mostly here it's Sentinel-2 data. So it's a little bit small here, but basically you have here a time series of 5 or 6 years of Sentinel-2 data. We calculate now an index, and here it's NDVI, it is the brilliant index, okay, so other index indicators, in fact, coming from different multispectral bands of Sentinel-2. And we look at the time series of this index, and how they change in time. And we apply by calculating the cumulated value of all this index, okay, we have a pattern in the time series. And when you have a shift like that, you see a drop here in the value of the different index. And in fact, it is a real change in the pattern, because, okay, you see it in NDVI, which is maybe the black time series here, and the red one is another index. You see that there is a combined shift here. So this means that, okay, it is really a signal. And when you look at the area, okay, at that time, okay, you had this triggering of landslide. So here it's, let's say, a detection of a red area within a green area of a forest. We are in Rwanda, so Central Africa. So it's, I mean, most of the landslide will be in that, you have some laterite which are red, okay, and you start from a green area, so it's relatively easy to detect. But okay, based on this approach, okay, you detect them, you have the real timing, the date, okay, and you have also the spatial maps according to that. So we move now in the system from to dates to time series analysis by applying other techniques, and this is currently released by this SCORE project that is currently being finalized over Rwanda.
Okay, thank you. And it's easy to make the difference with a deforestation event?
Yes, it is. Well, okay, there are still sometimes some bias between the two, but mostly it works quite well. Why? Because it will not be the same index that will change if you are in a deforestation system or if you have a landslide that is being triggered. Here we have a combination of index that are really mostly related to landslide. Okay, it could be another combination of index for the deforestation. Okay, and then you can also correlate that to the topography because if there is some deforestation, mostly it will be more or less on flat area. Okay, I mean, we will not do some deforestation on very steep slopes because it would be too costly, of course, to do the deforestation. So, so you can also use the topographic information to unbias the different data. Yeah.
Okay. And do you use in situ data or any other type of non-remote sensing data to validate the detection of the landslide?
No, we do not really use in situ sensor or such type of information. We have information, okay, because in some newspaper or in some reports or in social media, etc., there is an information that, okay, a landslide has been triggered over that area at a certain time. So, okay, we use it to validate, okay, but not to as a source of information to train the model or to train the time series analysis and constrain it. Okay, it's mostly for the validation.
Okay.
It's not a source of information, okay, in the method, let's say.
Okay, thank you, Jean-Philippe. I see we have questions in the chat.
Yes, and some people have, but then.
So we have a question from Malice Nema, right, Cecilia?
Yes, and Hervé Treboson and Riyad Abdel Fattah want to like to speak, I think.
Okay, maybe I propose that we start with the question from Malice Nema because I see it in the chat. Sorry, do you want to intervene or shall I read the question? So Malice is a PhD student based in Ivory Coast and working on landslides in the Kivu catchment of Rwanda. And so the question is, what would you advise for detecting landslides that are located in unreachable remote or reserved areas?
Okay, well, but in fact, that's typically such type of approach that could be used. Maybe I will just try, maybe to, yeah, should have done that before. In fact, I can try to, yeah. Okay. Yeah, maybe it's better like that. It's really, in fact, to possibly use this technique by okay calculating this time series of indicators coming from Sentinel-2 over the area and look at this change in the pattern of the time series. So this is the value of the spectral index. So this is in fact the cumulative value. This is the date of occurrence of the landslide. You see this shift, okay, in this drop in the value of the cumulated index for a landslide area affected here, okay. And if you go to a non-impacted zone, in fact, you do not see, in fact, this shift. So as I was mentioning before, because we do that on several index, we are pretty sure, in fact, that when we observe this drop, it means that we have a landslide. So you can easily make a first order inventory of the landslide and then map, because in fact this is an example of 1 pixel, but imagine you have several pixels. I should put a map here, but I did not have time to prepare it. But it's okay. You have a spatial map, in fact, so you can directly have an information about where the landslide is or not. So I would really suggest, in fact, to possibly test, in fact, this system for your PhD if you're interested.
Okay, thank you, Jean-Philippe. So, Mr. Riyad Abdel Fattah, do you want to ask your question also?
Yes,
okay.
Thank you for this opportunity you gave us to assist to this seminar. My question is on the feasibility of adapting the LHIS module, and in order to adjust it to take into account land subsidence. In fact, Tunisia, in the northeast of Tunisia, the Gabon region, we have a problem due to the overexploitation of underground water. And generally, this region is always subject to flooding, flash flooding in the rainy season. We have some confusion between the land subsidence and the land slides in the given parcels. My question is on the feasibility of adapting this.
Yeah, okay. So here mostly it's about landslide. So it's mostly about sediment along a slope. Okay, so it's a rapid movement. I mean, in the case of subsidence, where you have also a case of landslide, you have also an horizontal component of the displacement. Okay, in terms of subsidence, mostly you have just a vertical component. Okay, and in fact, the system here of detection is not adapted to that. For that, in fact, you really need to do some interferometric INSAR analysis to really construct time series of vertical displacement. Okay, so there are tools from satellite time series, mostly well from SAR satellite and applying INSAR techniques to do that. But the system is not done for that, for sure not.
Okay.
Okay.
Okay. Thanks for the question. Hervé Trebossen, please, you had the question, I guess, also.
Oui, merci. Thank you for the presentation. I am working as an external consultant for EU MedSat, so my question is more or less related to the precipitation products you are using. So you were saying that you were using mostly IMERG NASA products. Yeah. Did you try to... we are running various satellite application facilities at EUMETSAT, and one of those is the hydrology SAF, with maybe quite interesting product in terms of timeliness and also spatial resolution, because we are transitioning from 3 kilometers to 1 kilometers geostationary satellites. And so it's not a question, it's much more a comment, let's say. And we are also running the so-called no-casting satellite application facility that is also providing no-casting precipitation products. So it might be interesting because they are transitioning with the 1 kilometer resolution for
actually,
it's not the 500 millimeters from the NADA, but would be interesting.
No, I fully agree with you. I mean, it has to be tested. Okay, it is easily to implement because it is just a layer of information. I mean, from a technical point of view, it is easy to integrate because it is just one additional layer of information to feed the triggering module of the system. For instance, for the European use case in Swiss and in France, we are using estimate from Météo France for France. Okay, so it has been because we have the information and it's really high resolution. It's a combined information from in situ meteorology station and terrestrial radar information. So this SatLAMDO is directly integrated in the system. But at more global scale, I think it would be really interesting, in fact, to integrate the product of EUMETSAT, of course, and do some testing. It's from a technical point of view, there is no challenge. Okay, then maybe the triggering threshold that we will use will have to be tuned or calibrated, etc., etc. But that's it could be nice to do, for sure.
Thank you.
Okay. Thanks for this comment. Thank you, Jean-Philippe. Cecilia, do we have other questions in the chat?
Not in the chat, but we have Lesibat swelling. I don't know if you want.
Okay.
Okay.
Please feel free.
Thank you.
Okay. Hello.
To inquire because I realized that in the southern part of Africa, case where I think based on the assessment that we did during the disaster, where building structures seems to be the also contributors to the landslide. So I wanted to ask the presenter there, with regard to the model that you are using, have you factored the buildings, which could also be the contributors to landslide due to added load or altered drainage as well as slope modification in that area to the model?
No. Yeah, sure. No, it's a good point, but I mean, we are not working at that spatial resolution, and then some really, let's say, slope failure models, okay, where the exact circulation of water within the slope is modeled, or the excess loading coming from buildings or coming from even sediments coming to the slope could trigger landslide. This is not part of the analysis, because this would need much more complex model, much more data, much more parameters to tune them. And then we are entering into not a kind of regional assessment. It's more very local ones. Okay, so it could be something to envisage. Okay, but it will be changing the type of data we use as input, and we need also to change and use really process-based models, so physically based model to do the analysis. So that was not the ambition of the project.
Okay, no, but I see that you've got some good results. I think, yeah. Are they going to be formulating part of the training processes, which will be good for some of the models to be integrated locally here?
I did not get your question. You mean that you would be interested
sharing the models
in setting up
to check
sharing the models? Okay, or yeah, okay. Well, I mean the system is currently tuned for this 4 area I was mentioning.
Okay.
We start this analysis of our sub-region in South Africa. Well, so I don't know. I don't know the.
No. I think we are covered in that space. No, thank you.
Okay.
Thank you.
Okay, thank you very much for your question.
So may I have a question, please?
Yes, sure, son. Okay. Please go ahead.
Okay. Thank you, Jean-Philippe. Very nice presentation. I got one question about the model. So I saw that you use the model to estimate, to create the susceptibility map.
Mm-hmm.
Yeah. But I don't know, do you have any physical model or space analysis model for create this map?
You mean the data we use in the susceptibility model? That's the question?
Yeah, that's the method. I mentioned about the method. So
the method.
do you use physical method or?
No, it is a machine learning method here. Okay, to do some geostatistical approach. Okay, we know the past location of the past landslide. Okay, this is correlated to a certain slope, a certain land cover, a certain geology, a certain lithology, a certain distance to a fault, a certain distance to a river. Okay, so a lot of preconditioning factors. Okay, and we train an AI model. It is a random forest approach. Okay. To try to predict the future location with the similar conditions. So that's how we create the susceptibility maps of the source area.
Okay.
Yeah.
Okay, thank you. Very clear. One more question, please.
Yeah.
So what is the minimum area you can detect the landslide?
It is the prediction is done at 20 meters. So that's our resolution. Okay. So,
nice.
then most of the time, we try to aggregate a little bit. So at the end, the map is at 100 meters, but the original, let's say, calculation is done at 20 meters, and then to buffer a little bit the things. In fact, we make a production at 100 meters.
Okay, it's very detailed.
Yeah.
Okay. Thank you. It's clear. Okay, thank
you. Okay, you're welcome, son. Thank you for your question. And we have another question in the chat from Eugène Kayijimae. So you do want to ask your question, or I can read it also? Okay, I will read the question. So have you validated your results, for example, in the case of Rwanda? And if yes, what is the accuracy?
Well, we had so first we tuned the different rainfall thresholds, etc., and parameters of the services on past landslide event in Rwanda. I forgot now completely the dates, but we did it on 2 or 3, let's say, episodes of rains that have triggered several landslides in Rwanda. And then the system, since more or less 1 year and a half, is running with a daily prediction of the future occurrence of landslide. And we had some landslide episode last year. And okay, there was a relatively nice fit at first order. The main fit, as I mentioned, for Morocco, okay, that has been acquired for Rwanda. Okay, so yeah, we have some proof of evidence that it could work at first order. So yeah.
Okay, thank you. Cecilia, are there any other questions? Okay, please go ahead. I don't know who wants to speak. I can hear someone has opened the mic, but I don't know who. Okay.
Okay.
So maybe no. Okay, if there is no further question, I think it's time to say thank you to Jean-Philippe. Thank you also to all the participants. Jean-Philippe, just one last question. Are there any papers describing more in details the methods,
Yes.
for instance, for the landslide detection and so on?
There is one conference paper describing the method. I think it was in IGARS, the last IGARS EO symposium. I can share it with you, Linda, and
yes,
maybe
okay, and we will share
in your training pedagogical material system.
exactly.
Exactly.
And
we are currently writing a more science paper in a journal, in fact, with all the use cases, in fact. Morocco,
okay, great.
Alps, etc. So that is currently being submitted, in fact, for publication.
I would like just to have another last technical question regarding the cloud, the coverage, because you're using optical data, and some countries that are impacted by tropical countries that have a high cloud coverage. So is it a problem? Can it be a problem for your method?
Well, of course, it is an issue, of course. The point is that our approach, okay, that we need still to continue to work on is that, okay, we have a first order detection of the timing of the different landslide and the location with the Sentinel-2 time series. This is what I was mentioning with this indicator time series based approach with the NDVI, etc. of Rwanda. But then, because now we know exactly more or less where we have to look for the landslide, where they are located spatially, okay, and we have a kind of window time span of maybe 1 month or 1 month and a half, okay, where, okay, we detected landslide that occur over that period. We can then focus a SAR analysis using Sentinel-1, okay, just to do some change detection on this Sentinel-1 data, okay, not affected by clouds, okay, voila, okay, just to make some search over this limited, in fact, period of time and geographical area. So it's kind of two-step approach.
Okay, I see.
That's the idea. Okay.
Okay, that's very clear. Okay, so
I'm sorry, I got one question, please.
Go ahead, sir.
Sorry.
Yes,
so I think the model is very powerful and fully cover the landslide story. However, so the model is freely distribution or any commercial model or something? yeah, directly.
Is it open source?
How can I get?
Yeah, well, it's everything is open source. It's open source. It's open data. It's etc. But I mean, it is also attached to an infrastructure. In fact, to do the calculation. So the best, in fact, is to maybe request an access. I can share the link, in fact, with Linda later on, okay? And request an access if you want to use it, to use the system, and applying the service, in fact, by this approach, okay? Yeah.
Okay, thank you. Okay, thank you.
Okay, so thanks for your last questions, and thanks again to Jean-Philippe, thanks to all the participants, and we will share with you the replay of the webinar and also the references regarding the papers, the scientific papers related to the topic.
Yeah.
Okay, I see a question regarding the certificate of attendance. So please send us a message and I can issue a certificate of attendance if you need it. That. Okay, thank you, Alexis, for asking. Okay, so just a reminder that we will have our next webinar on the 10th of April dedicated to mangrove monitoring. So we will disseminate the announcement also. So it will be at the same time, 10 o'clock a.m. in Europe. So we are changing the time in France. So I guess in Vietnam, for instance, it will be like 3 p.m. But I will send, and in Africa also there will be maybe a change in the time zone. But I will send the announcement with the so that you can register to this webinar on mangrove monitoring. Okay, so thank you very much to all, and so wishing you a nice weekend ahead. And merci Jean-Philippe.
Merci à vous.
Okay, goodbye.
Bye bye.
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 Thank you. Bye.